Hello. Today we're going to look at equations and inequalities which contain absolute values. Let's take a look at our objectives for the day. First, we want to be able to solve absolute value equations by using the distance definition. We want to solve absolute value equations algebraically. We want to solve absolute value inequalities by using the distance definition. We want to solve absolute value inequalities algebraically. And we want to solve absolute value inequalities that require a transformation. We want to solve special cases of absolute value equations and inequalities. And we want to solve absolute value inequalities to describe distances. Now recall the definition of absolute value. Absolute value gives the distance from A to 0 on a number line. Now we can use this definition to help us solve the equation, the absolute value of x equals 5. Now we know that x is 5 units from 0 on a number line. So if we look at our number line, we find that we have two values that are 5 units from 0. So our two solutions are -5 and 5. And here's our solution set, which contains the two solutions to our equations. Now, let's look at the distance between any 2 points A and B on the number line. These distances are given by either of these two absolute values, the absolute value of A minus B or the absolute value of B minus A. We can use this idea to solve an equation that looks like this. The absolute value of x minus 2 is equal to 4. Now what this is telling us is that the distance between x and 2 is equal to 4. Let's look at this on a number line. Here we have a number line. We're primarily interested in the number 2 and those numbers that are 4 units from 2. Those two numbers are -2 and 6. These two values, -2 and 6, give us the solution set to our absolute value equation. Now, we need to look at some rules for simplifying absolute value equations. First, for b greater than 0, the absolute value of a equals b if and only if a is equal to b or a equals the opposite of b. Our second rule tells us that if we have the absolute value of a equals the absolute value of b, then this is true if and only if a equals b or a equals the opposite of b. Now let's look at an example here that involves the first type of absolute value equation. We want to solve the absolute value of 5 minus 3x equals 3. Now we know that 5 minus 3x must be 3 units from 0. So 5 minus 3x equals 3, or 5 minus 3x equals -3. Now solving the first equation, we have -3x equals -2, or x equals 2/3. And solving the second equation, we have -3x equals -8, or x equals 8/3. So our solution set consists of these two values, 2/3 and 8/3. Now let's look at an equation of the second type. We want to solve the absolute value of 2k minus 3 equals the absolute value of 5k plus 4. 2k minus 3 equals 5k plus 4, or 2k minus 3 equals the opposite of 5k plus 4. Solving the first equation, we find that 2k equals 5k plus 7, -3k equals 7, or k is equal to -7/3. Solving the second equation, remember we must distribute the negative sign. We have 2k minus 3 equals -5k minus 4. 7k equals negative 1, and finally, k equals negative 1/7. So our solution set consists of the two numbers negative 7/3 and negative 1/7. Now here's a problem for you to solve on your own. We'll pause the tape and give you a chance to do that. Let's look at our solution to this problem. We have x plus 2 equals 3x plus 8, or x plus 2 equals the opposite of 3x plus 8. Solving the first equation, we have x equals 3x plus 6, or negative 2x equals 6, or x equals negative 3. Solving the second equation, we have x plus 2 equals negative 3x minus 8, 4x equals negative 10, or x equals negative 10/4, which reduces to negative 5/2. So our two solutions here are negative 3 and negative 5/2. Now, our definition of absolute value can be extended to solve absolute value inequalities also. If we look at the absolute value inequality, the absolute value of x is less than 3, then we're looking for all real numbers whose distance from 0 is less than 3. If we look at our number line, we recognize that all the numbers between negative 3 and 3, excluding the endpoints, have a distance which is less than 3. So we see that all the numbers in the interval from negative 3 to 3 would satisfy this inequality. Now we could also have an absolute value inequality with a greater than sign. Here we have the absolute value of x is greater than 3. Now we're looking for all those values of x which are more than 3 units from 0. Looking at our number line, these would be all the numbers to the left of negative 3 and all the numbers to the right of 3. Now, keeping these ideas in mind, we have two more properties of absolute value that we can look at to solve inequalities. For any positive number b, our first property states the absolute value of a is less than b if and only if a is greater than negative b and less than b. Our second property states that the absolute value of a is greater than b if and only if a is less than negative b or a is greater than b. Now let's apply these properties to an inequality. We want to solve the absolute value of x plus 1 is less than or equal to 3. Now this is telling us that x plus 1 must be between negative 3 and positive 3. And that's from our first property. Now we can finally solve this problem by subtracting 1 from each of the 3 parts, giving us that x is greater than or equal to negative 4 and less than or equal to 2. In interval notation, remember, our solution set is the interval from negative 4 to 2, and this is a closed interval. Please note that what we're saying here is that x is within 3 units of negative 1. Let's look at this on the number line. X, which can be any number between negative 4 and 2, is within 3 units of negative 1. Remember that x plus 1 is equal to x minus a negative 1. Let's look at this example. This time we'll look at a greater than example. We want to solve the absolute value of 3z plus 1 is greater than or equal to 7. This tells us that 3z plus 1 must be less than or equal to negative 7, or 3z plus 1 must be greater than or equal to 7. Solving each one, we have 3z is less than or equal to negative 8, or 3z is greater than or equal to 6. And dividing both by 3, we have z is less than or equal to negative 8/3, or z is greater than or equal to 2. Looking at this in our set notation then, we're looking at all the values of z that are between negative infinity and negative 8/3, including the negative 8/3, and all values of z greater than or equal to 2, so that would be the interval from 2 to infinity, including 2. Now notice that in both of these problems that we had an absolute value isolated on one side of the inequality sign. Now here's a problem where the absolute value is not isolated. We have this 4, and we have this 2 over here, which we're subtracting. In order to use our properties, we first must isolate our absolute value. So the first thing we want to do is to add 2 to both sides of the inequality. And then we want to eliminate the 4, so we'll multiply both sides by 1/4. This gives us the absolute value of 5x plus 1/2 is less than 2. And we have successfully isolated the absolute value. Now, we can rewrite this as negative 2 is less than 5x plus 1/2 is less than 2. Why don't we pause the tape here and let you try to complete this problem? Let's look at the solution to this inequality. First, we need to subtract 1/2 from each part of the inequality, and then we need to multiply each part by 1/5. This gives us negative 1/2 is less than x is less than 3/10. So the solution to our inequality can be written as the open interval from negative 1/2 to 3/10. Now here's a problem for you to try. Notice in this case you have to do a transformation first. All right, let's look at our solution. Did you remember first to multiply both sides by 1/5? This gives us the simple inequality, the absolute value of x minus 2 is greater than 4. Now we can use our properties for inequalities and write this as x minus 2 is less than negative 4, or x minus 2 is greater than 4. And solving both of those, we find that x is less than negative 2, or x is greater than 6. So our solution set then is given by the interval from negative infinity to negative 2, union the interval from 6 to infinity. Now when you're working with absolute value equations and inequalities, remember the primary thing is to think. Let's take a look at these 3 problems. And I'm going to pause the tape and let you try to solve them. All right, did you find that there is no solution to the first equation? Here we're trying to say that the absolute value, which we know is not negative, equals a negative number. So there is no solution here. Our solution set is represented by the empty set. In the second case, regardless of what x is, the absolute value is always greater than or equal to 0. So our solution set is the set of all numbers from negative infinity to infinity. In the third case, we have an absolute value equation, but we have 0 on one side, so we have just the one solution, x equals negative 3/2. Now we can use absolute value definitions to help us write statements which involve distance. Here's an example. We want to write r is 5 units from 3. To do that, remember we're saying that the distance between r and 3 equals 5. And we would say that as the absolute value of r minus 3 equals 5. Now here's another statement. P is at least 5 units from negative 9. Now we're saying that the distance between P and negative 9 is at least 5. And we would write that as the absolute value of P plus 9 is greater than or equal to 5. Remember, P, take away a negative 9, is P plus 9. And finally, if we have the statement M is no more than 8 units from 9, we would write this as the absolute value of m minus 9 is less than or equal to 8. Now, we can also look at some applications which involve absolute value inequalities. Here's the problem for us. In one winter month in Chicago, the daily low temperatures in degrees Fahrenheit satisfied the inequality the absolute value of T minus 15 is less than or equal to 10. Find the range of low temperatures that month. Well, this is an absolute value inequality, and we know that we need to rewrite it that T minus 15 will be between negative 10 and plus 10. Now, to solve this three-part inequality, we simply add 15 to each part. Our solution set then gives us the set of low temperatures which ranged from 5 degrees Fahrenheit to 25 degrees Fahrenheit. Now, let's take a look at this problem where we would like you to write this statement as an absolute value inequality. We're going to pause the tape and see what you can do with this. Okay, x is within 4/100ths of a unit of 2, then y is within 1/1000th of a unit of 7. So we would write if the absolute value of x minus 2 is less than or equal to 4/100ths, then the absolute value of y minus 7 is less than or equal to 1/1000th. Well, we have covered a lot of material again today involving absolute value equations and inequalities. Again, try to practice as much as you can so that you learn these skills. Have a good day.